Santa Video. Efficient video generation with block linear diffusion transformer.
Right out the gate with the title, I love it.
Yeah, we are jumping straight in today because this paper is, well, it's a massive deal. We are looking at a fundamentally new, highly efficient, small diffusion model, and it generates up to 720p minute-long videos directly on consumer hardware.
Which is wild to even think about.
Right. Specifically, this is running on a single RTX 5090. And the NVIDIA research team pulled this off by completely replacing the standard super expensive ON squared vanilla attention mechanism. They swapped it for a linear diffusion transformer or DIT architecture.
And they utilized a constant memory KV cache for block linear attention, which is basically the secret sauce here.
Exactly. And the economics of this are just staggering. I mean, it took only 12 days on 64 H100 GPUs to train.
Wow.
Yeah, that is roughly 1% of the compute cost of training a massive model like MovieGen.
Just 1%. That's a rounding error for some of these big labs.
Truly. Yet despite that tiny compute budget, Santa Video outperforms or, matches much heavier models like the 2.1-1.3B, and it renders at 16 times the speed.
So for those of you listening who caught our recent video on AI paper slop covering Santa WM, you'll probably remember that world model added exact 6 degree of freedom camera control, right, for environment simulation.
Yep, the dual branch camera control.
Exactly. But to truly understand how Santa WM managed that massive efficiency without just completely crashing an entire GPU cluster, we have to look at the engine underneath it.
Right. So if Santa WM gave us the steering wheel and the spatial control, Santa Video essentially built the actual powertrain.
That's a great way to put it.
Because the core problem this architecture solves is the prohibitive token count in modern video generation. I mean, if you are an ML engineer working in video, you know that sequence length is your absolute worst enemy.
Oh, it's the ultimate bottleneck, no question. Because we look at current state-of-the-art models, the computational math is just brutal.
Right. Walk us through that math.
So take a widely used model like 114B. To process just a 5-second video at 720p resolution, the model has to crunch over 75,000 tokens per frame iteration.
Which is a massive amount of data to hold in memory.
It is. And because traditional self-attention has a computational complexity of ON squared, the processing time scales quadratically with every single token you add.
So it's not a linear increase, it's an exponential explosion.
Exactly. To visualize that, if 75,000 tokens is ON squared, the model is calculating over 5.6 billion attention interactions per layer.
Wait, per layer?
Per layer. Now expand that video from 5 seconds to a full minute, and you are suddenly dealing with trillions of interactions. The GPU memory just instantly redlines.
Yeah, you just hit a wall.
Right. Just processing those 75,000 tokens through standard attention layers takes about 32 minutes on a single H100 GPU.
32 minutes for 5 seconds of footage. That is, well, it just shows that ON squared complexity means standard attention is fundamentally broken for long-form video.
It really is. It just doesn't scale.
It's like, imagine a massive crowd in a room, right? Standard attention is like everyone in that room having to stop and shake hands with every single other person.
That would take forever.
Exactly. It causes this exponential explosion in interactions. But linear attention, which is what Santa Video uses, is more like a relay race.
Okay, I like that analogy.
Yeah. So each runner just passes a single baton forward. The baton accumulates all the necessary mathematical information as it goes. So the 100th runner only has to look at the baton. They don't have to run all the way back and talk to the first 99 runners.
Right. So the scaling becomes completely linear, or ON. The efficiency gains there are just massive. The scaling curve goes from this steep, terrifying hockey stick to just a nice flat diagonal line.
But wait, let me push back on that for a second. If linear attention is so efficient because it's only looking at that one compressed baton of information, doesn't it lose track of the fine local details?
That is the million-dollar question.
Because you don't have that dense pixel-by-pixel, frame-by-frame mapping of standard softmax attention, it feels like you would lose the microtextures, like the ripples in water or hair moving.
You're spot on. That is the exact trade-off the researchers had to solve. Vanilla linear attention can absolutely be too global.
It just smears everything together.
Yes, it has a very well-known tendency to blur local textures and lose high-frequency details because it's basically averaging things out over the sequence.
Right. So how did they fix it?
So to fix this, Santa Video made several highly specific architectural modifications. First off, they dramatically widened the pipeline.
Okay.
For context, standard models in this weight class might use a feed-forward network dimension of like 2 or 4,000. Santa Video bumped that FFN dimension all the way up to 6720.
Oh, wow, that's a huge jump.
And they bumped the head dimension up to 112. They essentially gave the network the sheer parameter capacity to remember those high-frequency details that linear attention might otherwise just smooth over.
Okay, so they basically brute forced the capacity of the pipes, so the linear attention wouldn't bottleneck the visual fidelity.
That handles the raw capacity, yeah. But they also needed robust spatial and temporal awareness. So they integrated 3D Rope E.
Which stands for rotary position embeddings, right?
Exactly. Because standard absolute positional embeddings, they just assign a static number to a token's position.
Yeah.
But Rope E, instead, rotates the token representations in this complex mathematical space.
Okay, so it's mapping relationships better.
Yes. Mathematically, this rotation preserves the relative distance between tokens much better than just static numbers. And by making it three-dimensional, the model inherently maps out the spatial layout, so the height and width of the image as well as the temporal axis of time.
So it knows exactly where a pixel is in 3D space across time.
Right, which drastically improves the model's ability to handle long context relationships without blurring the geometry of the scene as the frames progress.
But to explicitly force the model to care about the local details, they also added a 1D temporal convolution to the mixFFN layer, didn't they?
Yes, they did. And they did this via a shortcut connection.
Right, so while the linear attention is looking at the broad global picture, like the baton in our relay race, this tiny temporal convolution is acting like a magnifying glass.
Exactly.
It scans across the immediate time axis to ensure that the immediate frame-to-frame motion of, say, a subject's hand or the rustle of a leaf remains perfectly crisp.
And the shortcut connection there is vital. It allows the temporal convolution to seamlessly capture those local relationships along the temporal axis without destroying the pre-trained weights of the base model.
It's a very elegant division of labor.
It really is. The linear attention handles the global context efficiently, and the temporal convolution refines the local frame-to-frame motion perfectly.
Okay, so that perfectly explains how they can process 5-second videos so fast. But the paper claims it can generate a full minute of 720p video.
Yeah, 60 seconds.
I mean, even with linear ON scaling, 60 seconds of high-definition video is a staggering amount of data. How do you scale to those extreme lengths without your VRAM just completely redlining?
So the answer lies in a component they call long Santa. And the mechanism behind it is a constant memory KV cache, which is enabled by block linear attention.
Okay, break that down for us, because the KV cache is a huge issue in ML right now.
It is. So in the standard transformers, the key value, or KV cache, has to store the history of all previous tokens to maintain context.
Right.
As your generated video gets longer, your KV cache grows linearly. So eventually it just consumes all available GPU memory.
The cache bloat is infamous. You generate 10 seconds, your cache footprint is X. You generate 60 seconds, your cache is 6X, and your GPU just throws an out-of-memory error and completely crashes.
Santa Video leverages the cumulative properties of causal linear attention to bypass this entirely.
Okay, how?
Because of how the linear attention formula is mathematically structured, you do not actually need to store every single past token.
Wait, really?
Yeah, you can compress all that historical context into a single fixed-size running state. They process the video block by block. So for every new block of video generated, they simply update this fixed memory state rather than appending new tokens to an ever-growing list.
Oh, wow. So the memory footprint is completely flat.
Entirely flat.
Whether you are rendering the second of the video or the 59th second, the computational cost and the memory usage for each new token remains mathematically identical.
Exactly. It operates with a constant memory KV cache, which is what makes minute-long generation possible on consumer hardware. You never hit that memory wall.
That is a massive paradigm shift for inference.
Yeah.
And there's always generating long sequences autoregressively, where you generate chunk by chunk, that introduces another major hurdle, right? Exposure bias.
Ah, yes. Exposure bias.
Because if you have a tiny, almost invisible pixel artifact in block 1 and you feed that into block 2, it amplifies.
It's a snowball.
Yeah, by the time you get to block 10, the model is trying to condition its generation on pure garbage, and your video turns into a mutated, unrecognizable blur.
It is the classic compounding error problem. Because in autoregressive generation, there's a domain shift between training, where the model sees perfect, pristine ground truth frames in inference, where the model sees its own slightly flawed predictions.
So how did they stop the 60-second video from turning into an abstract painting by second 45?
They designed a highly specialized two-stage post-training paradigm specifically to unlock this infinite length generation.
Okay.
The first stage is an improved self-forcing block training. So normally you use teacher forcing, right? Feeding the model perfect ground truth pass frames to predict the next frame. But in self-forcing, they selectively expose the model to its own generated frames during the training process.
Oh, I see. So you're basically teaching a driver how to correct a skid rather than just letting them practice on perfectly dry pavement forever.
That's a perfect analogy.
Oh, they learn how to recover from their own minor deviations before those deviations can snowball into a crash.
That is the exact mechanism. They learn the recovery distribution, and then they pair that self-forcing with a monotonically increasing SNR, or signal-to-noise ratio, sampler.
What does that do?
As the autoregressive generation moves further in time, the SNR sampler actively ensures that the noise levels across the sequential blocks remain mathematically consistent. It acts as a stabilizing anchor.
So it prevents the latent representation from drifting into chaos as the sequence gets longer?
Precisely. Together, the self-forcing and the SNR sampler cure the exposure bias that usually kills long context video generation.
Okay, so with exposure bias solved, the architecture is mathematically sound. But brilliant math usually requires a massive compute budget to train.
Usually, yes.
Yet, as we mentioned at the top of the video, the NVIDIA team trained this on just 64 H100s in 12 days. That 1% compute metric compared to movie gen is just wild to me. How did they bypass the multi-million-dollar compute wall?
The secret to that training efficiency is their initialization strategy. Santa Video did not start from scratch.
Because learning the visual world, physics, lighting, textures, human anatomy from zero takes massive amounts of compute.
Exactly. They bypassed that by initializing the model from the pre-trained Santa 1.6b text-to-image model.
So they took a foundational image model that already understood what a dog looks like, what a sunset looks like, what a camera lens flare looks like, and they just taught it how to move.
Exactly. And the critical engineering detail here is how they integrated the movement. When they inserted the new temporal layers, like that 1D temporal convolution we discussed earlier, they zero-initialized those layers.
Zero initialized. Why?
And they added skip connections around them. Initially, these new layers output exactly 0. This means the network functions identically to the pre-trained image model on day 1 of training.
Oh, that's clever. So it doesn't suddenly forget how to draw a dog just because you asked it to make the dog walk.
Right. Over the course of the training run, these temporal layers slowly wake up and learn temporal dynamics without suddenly disrupting or destroying those pre-trained image generation capabilities.
And their curriculum for training this model is honestly a masterclass in efficiency because they used a course-defined strategy.
Yes, the scaling strategy.
They started by training the model on low-resolution, 192p videos that were only 2.5 seconds long. And then once the model mastered the basic physics of motion at that tiny level, they scaled up the resolution and duration to 480p 5-second videos.
Because generating motion at 192p involves moving far fewer pixels. It allows the model to grasp the broad optical vectors before worrying about high-resolution microtextures.
It is exactly like an athlete doing low-weight, high-repetition motion training to nail their mechanical form before they ever attempt to lift heavy. You do not start with the heavy weights. You start with the mechanics.
That's a great way to think about it. But, we cannot discuss this training efficiency without looking deeply at their data curation.
Oh, definitely. Garbage in, garbage out.
Right. If you feed a highly efficient model garbage data, your architecture will just learn how to generate garbage extremely quickly. So the team engineered a meticulous data filtering pipeline.
What did that look like?
To ensure the model learned precise text-to-video alignment, they used a strong vision language model, or VLM, to generate incredibly dense captions for the training videos. We are talking 80 to 100 words per caption.
Wow, that is dense.
Detailing everything from subject appearance to background elements to exact camera angles.
I mean, detailed captioning is somewhat standard practice now, but what really caught my eye in this deep dive was how they mathematically handled motion filtering.
Oh yeah, this is fascinating.
Because if a training video is just a static shot of a building, the model learns nothing about movement. But if the video is a chaotic, shaky cam action scene, the model just learns blurry noise. How did they define the boundary between good and bad motion?
They mathematically separated the motion by evaluating 2 different vectors of movement. First, the team used a tool called Unimatch to evaluate the optical flow between frames.
Okay, optical flow.
Right, so optical flow measures the specific directional vector movement of objects within the scene. For example, a car moving left to right across the frame. Then they use a metric called VMAF to compute pixel differences.
And that measures what?
That gives a sense of global scene change, like a camera panning or a massive lighting shift.
Ah, so they cross-referenced the specific object movement from Unimatch with the global pixel changes from VMAF to create a reliable mathematical boundary.
Exactly. This let them filter out videos where the motion was either imperceptibly slow or aggressively fast.
And they didn't just filter it, they took that calculated motion value and actually appended a specific tag, like motion score, directly to the text prompts during the training phase.
They explicitly taught the model the correlation between a text string and a mathematical magnitude of motion.
That is brilliant. That means at inference time, you, the user, have explicit control over the motion magnitude just by tweaking the text prompt.
It gives you a highly controllable latent space. The model inherently understands what a high-motion text prompt means geometrically.
Okay, so theory and training efficiency are great, but benchmarks pay the bills. Let's look at the performance metrics.
Do it.
On the vBench evaluation suite, Sana Video hit a text-to-video score of 83.71. For context, that score matches massive 14 billion parameter models, despite Sana Video being a fraction of the size.
It's punching incredibly far above its weight class.
Seriously. And on image-to-video generation, it hit an 88.02.
And a key reason for that visual fidelity, especially at high resolutions, is their autoencoder strategy. For 480p videos, they utilized the WAN 2.1 VAE. But to handle the jump to 720p, they fine-tuned a deep compression autoencoder, which they refer to as DCAEV.
Okay, so how does that help?
This allowed them to compress the high-resolution spatial and temporal data into a dense latent space. Instead of computing diffusion on millions of individual pixels, the deep compression autoencoder shrinks the video down into a highly dense mathematical grid. The small diffusion model works its magic efficiently on that tiny grid, and then the decoder inflates it back up to crisp 720p video without losing visual information.
Okay, wait. If we are talking about running a high-resolution, long-context video model on consumer silicon, specifically the RTX 5090, we have to talk about quantization.
We do.
Because the researchers used a framework called SVD Quant to quantize Sana Video down to the NVFP4 format, which is a 4-bit floating point format.
Yep, 4-bit.
But if you aggressively quantize a diffusion model down to 4-bit, doesn't that completely destroy the semantic quality? I mean, usually the video gets noisy, the colors bend, the geometry warps. You save memory, sure, but you ruin the final product.
If you apply a naive blanket 4-bit quantization across the entire model, you are absolutely right. It breaks the architecture.
So what do they do differently?
Outliers in the activation channels usually ruin 4-bit quantization. But Sana Video uses selective quantization. They profiled the neural network to see which specific layers could handle low precision and which layers were fragile. Yeah, so they applied the aggressive 4-bit quantization to the QKV projections and the output projections within the attention layers. Those specific dense layers are highly robust to precision loss.
Okay, but what about the rest?
They kept the normalization layers and the temporal convolutions at a higher precision like BF16.
Right, because normalization layers handle the scaling and shifting of the entire mathematical distribution. If you lose precision in the norm layers, the errors compound exponentially through every subsequent layer of the transformer block.
Exactly. By keeping those sensitive distribution layers in higher precision, they avoided the outlier accumulation that usually breaks quantized models.
That makes total sense.
Yeah, they maintained the semantic quality of the baseline model while vastly reducing the memory footprint of the heavy projection layers.
And the speed up from this.
The result of this selective NVFP4 quantization is staggering. Generating a 5-second 720p video drops from 71 seconds down to just 29 seconds on a single RTX 5090.
Wait, 29 seconds? That is a 2.4x speed up with virtually zero mathematically measurable loss in visual fidelity.
It's incredible.
It fundamentally changes what is possible on local hardware. For those of you who watched our recent AI paper slot video on Sana WM, this is exactly why we needed to do this deep dive into the Sana video source material today.
It's the foundation of everything they built next.
Exactly. This exact efficiency, the linear DiT drop in complexity to ON, the constant memory KV cache allowing for massive sequence lengths without exploding VRAM, this is the underlying engine.
Sana Video proved the underlying math worked. It proved you could model long horizon temporal data efficiently. SandWM simply took this exact foundational architecture and built a world model right on top of it.
Yep.
They added their dual-branch camera control and metric scale 60F pose supervision. SandVideo solved the memory and compute bottleneck first, and that freed up SandWM to focus entirely on perfect spatial geometry and user control.
It is such a brilliant example of foundational research enabling an immediate leap in applied capabilities. And honestly, it forces us to look past just video generation.
Oh, definitely.
Because if a model can maintain perfect infinite state memory for pixels on a cheap consumer GPU,
Consider what happens when this ON constant memory scaling scales beyond visual data.
right?
Imagine applying that same flat memory architecture to long-form, continuous agentic memory, or real-time robotics operating indefinitely in the physical world, or even infinite game engines and live interactive simulations where the video never actually ends.
The constraint is no longer the hardware memory limit. The constraint is simply what we choose to generate with it. It's a whole new paradigm. Well, thank you so much for joining us for this deep dive on AI Paper Slop. Keep building, keep experimenting, and we'll see you in the next one.